coordinator in this workshop. And good morning to everyone. My name is Dr. Vikash Gurugubelli. I am former scholar and I was working under the Professor Arnab Ghosh sir. And coming to the today's topic, modeling, analysis and design of droop controlled parallel voltage source inverter. And not only droop, I will cover some virtual synchronous machine based voltage source inverters and virtual oscillator control based. And I will use some artificial intelligence and machine learning based controllers to control the voltage source inverters. And coming to the introduction, the electricity demand is increasing day by day due to several reasons, due to economic growth, industrial development, and high domestic uses. And it is very difficult to meet this demand by using conventional power generation because they are depletable and they emit greenhouse gases. So, in order to address this issue, renewable energy sources are the key role. So, by using renewable energy sources, we can meet this demand. And coming to the new interface, actually, the conventional power system is dominated by the mainly synchronous generators. But here, the new power system will emerge uh, by using inverters. So we will use renewable energy sources, and we need to connect these renewable energy sources to the AC grid. So inverter is the only solution. So to connect to the grid. So here we will replace, not only replace, we will by using renewable energy sources, we will use inverters to connect to the grid. And it is very difficult to design a, suppose our conventional synchronous generators rating is around 210 megawatt, 500 megawatt. But in case of inverters, the maximum rating of the inverter in India, we are using around 0.3 megawatt. So we need to scale. Suppose it is a some 20 megawatt plant. In suppose that is a synchronous generator. So we have to scale accordingly. So we will use number of inverters parallelly. Then we will match that conventional synchronous generator. And this is the scaling. And coming to the location, actually the synchronous generators are very far from the end users. But in case of by using renewable energy sources, it is medium voltage level or low voltage distribution. So we can avoid the transmission losses by using inverter based power generation. And coming to the power system architecture, the left side one is the Okay, the left side one is the present power system architecture, but in future we will meet the excess demand by using renewable energy sources. Here the green color is the inverter based power generation. And coming to the implementation. So for implementation, suppose here it is showing PV panel. It is nothing but one renewable energy source. So inverter is a device which convert DC power into AC. So here the DC power may come from renewable energy sources like solar and fuel cells. So many renewable energy sources are available. So we cannot connect that renewable energy source directly to the grid. So here in case of solar, the solar output is DC in nature. So we have to convert the DC power into AC. Then only we can connect to the grid. So the inverter is the inevitable device. So the inverter plays very crucial role in the um, renewable energy sources. So here it is the basic implementation of the inverter. It is a simple inverter and connected to some renewable energy source, and we will use some filter to reduce the harmonics. And here it is like a sensor. So and this is one microcontroller to control the our inverter. And here coming to, actually here my main idea is actually grid forming inverters. So Grid forming inverters means actually now our synchronous generators are connected in parallel. So they will follow the Droop law. So if the load active power or reactive power is changing at the point of common coupling, okay, accordingly the inverters will share their uh, powers. So here also our inverter should mimic the synchronous generator. So that is the main idea. So for that we need to control that inverter in such a way that it will act like a synchronous machine. So this is the simple single phase inverter with LC filter, and we can connect to grid, or we can operate in islanding mode. So first I will explain how to control this inverter in grid connected mode and islanding mode. So in grid connected mode is easy compared to islanding mode, because in grid connected mode, so from the PLL it can get the voltage reference and um, phase angle from the PCC. But in case of islanding, we have to give the voltage reference and frequency reference and phase angle. All these things we have to uh, give to the controller. So here first I will explain how to control in islanding mode. And in case of grid connected mode, we have to give the reference active power and reference reactive power. So accordingly, it will inject that much power into the grid. That's it. But in case of islanding mode, we don't know the load. Based on the load, the inverter should provide that power to the load. So that is the difference between islanding and grid connected. So actually in India, most of the inverters are grid following. Grid following means if the power in the grid is there, then only it can inject some power into the grid. If there is grid outage, if there is no power in the grid, it will be ideal. It will not give any power to the grid, and it will not give any power to the local also. So that is the drawback. But in case of grid forming inverters, these all inverters will form a grid independently. In case of grid following inverters, there should be power in the grid. Then only it will inject some power into the grid. Otherwise, it will be ideal. That is the difference between grid forming and grid following inverters. Okay, now I am going to explain the control of grid, just simple inverter operated in islanding mode. Okay, so if you my suggestion is you just try to remember this structure of the system. Here one DC source is there, and here one DC link capacitor to reduce the fluctuations in DC side, and here is it is the three-phase voltage source converter. It is three-phase filter, and this is the filter capacitance, and this is the filter inductor, and this is the internal resistance of the inductor, and remaining are the just control. So you just we remember this just power, not signal level, at least remember this power level diagram, then only you can understand these equations. So if we apply KVL across three-phase filter, we can get this equation 1. See, it is simple, VTA minus VSA. If you see, this is here, the voltage drop, VTA minus VSA is nothing but this is this IA into RF plus RR plus LF into DIA by DT. Okay. And if you apply traditional DQ frame control, before that, why we are converting this ABC to DQ? So in case of ABC, these all signals are IA, IB, IC. If you by using current sensors, if you measure this IA, IB, IC, these all are in AC in nature. So The PI controllers, what we are used in the inner control loops and the outer voltage control loop. In this inner current and voltage control loops, the PI controllers are unable to track this. What is that? AC signals, AC sinusoidal signals. So in case of if the signal is DC, the PI controllers um, will be operate very nicely compared to AC signal. In case of AC signal, the PI controllers efficiency or the PI controller tracking is not good compared to DC. That's why we are transforming the three-phase signals into traditional DQ frame. And by using ABC to DQ transformation, I will get this equation 2. And after performing Laplace transform, then we are applying Laplace transform, then we can get equation 3. And in order to decouple the dynamics, the modulation index, the equation 4, from the diagram you can understand. I will show one control, what is that? I will show the inner current control loop and voltage control loop. There you can clearly understand how we are what is the designing this MD and MQ. These are the modulating signals. These are very important. So here modulating signals means the controller is mainly controlling this MD and MQ only. So based on this MD MQ, we will get the output voltage. See here the output voltages in DQ frame can be represented in equation 5. See here the VDC is the input and VTD is the output. But what we are controlling is just MD. So if we control this modulating signal, then we accordingly we will get the output voltage. So here the control signals are MD and MQ. Okay. And coming to the next slide. Yes. This is the control block diagram of current controlled voltage source converter in the DQ reference frame. See, this is the equation, I think equation 3, equation 4, equation 5. So here the red box shows the AC side dynamics. So already we have applied KVL across the VTA and VSA. There we can get some dynamics. See here after Laplace transform, these are the this red box shows the AC side dynamics. These are the physical equations. Okay, so with these equations we cannot change. But in remaining this red box, this green box also, this is just converter gain. We cannot. This is not in our control. So we are generating from the controller. See here, DQ frame current controller is giving the MD and MQ. So in the controller, we can change or we can manipulate anything to get the best result. Okay. See here, in this controller, if you observe, here we have two PI controllers, KD and KQ. So already I told you, first we convert ABC to DQ transform to get to transform AC signals into DC in nature. Then only our PI controllers work properly compared to AC signal. And here we are decoupling. Decoupling means here see our here ID is depending upon the IQ of S. So first we have to decouple, then only we can get the simple transfer function. If it is coupling is there, it is difficult. It is actually this whole system is multi-input, multi-output system. See here the inputs are ID reference and IQ reference, and the outputs are ID of S and IQ of S. First we have to decoupling this ID and IQ. Here also IQ and ID. So see, if we see this blue box, in this blue box we have implemented the controller. Here if you observe, this ID reference is the actually suppose it is a grid connected mode. So we have to inject some active power and reactive power into the grid. Based on the active and reactive power, we can calculate the ID reference and IQ reference. From that ID reference and IQ reference, we will what is that, inject the same power into the grid. Okay. So here ID reference and IQ reference we will fix. Okay, then we actual ID, it is the feedback and we are measuring, then the error is given to the one of the PI controller. Okay, see here from this in AC side dynamics there is a coupling. suppose here ID of S equal to this here C. This is VTD of S minus VSD of S plus C plus this LF omega into IQ. Okay, this is the red box shows the equations. Here the coupling between ID and IQ. So if you see this control law here, we are by using this technique, decoupling technique, we are simply eliminating the coupling between the ID and IQ. Then this multi-input and multi-output system converted into single input, single output system. See, so by using decoupling method, we are simply converting that whole system into two single input, single output system. So from this, we can easily get the transfer function, and we will easily uh, design the controller. Otherwise, it is for multi-input, multi-output system, it is very difficult to design the control parameters. Here, the control parameters is in this here KDI is nothing but one PI controller. Here KP and K are the control parameters. So once it is we are decoupling the ID and IQ, so we are simply getting the single input, single output systems with simple PI controller. Now we can easily design the KP and KI. See here the KP plus KI by C. This is nothing but PI controller. And the open loop gain, if you observe in the closed path, this is the equation 7 shows the open loop gain, open loop gain. So if we observe the KIC and KPC is equal to this RF plus R1 by LF, then we can pole zero cancellation. So that is one of the advantage. By using that cancellation, we can easily design the KP and KI. So finally, the closed loop transfer function is shown in equation 9. Okay. So where Ti is the desired time constant for the closed loop system, and it can be represented in equation 10. And from above that, we are simply designing that Kp and Ki. Here the Kp is depending upon the filter inductor and time constant. The filter inductor, we are already we first before designing the inverter, we have to design the filter also accordingly. So once we know the filter inductor values, this filter resistance values, and we know, we will fix the desired time constant. First, how much what is the desired time constant? Suppose I want some 1 milliseconds or 10 milliseconds. Accordingly, the system will respond. So here, see, the typically the range of the time constant is 0.5 to 5 milliseconds. So but I'm considered some time constant is 1 millisecond, and I consider some roughly some values of LF and RF plus RN is 32 milliohm accordingly. So so this LF and this filter parameters and desired time constant we know. So from that we can easily calculate the PI controller gains Kp and Ki. Those are shown in equation 12. And coming to PCC voltage controller. So first here, if it is grid connected, just the current control loop is enough to control the inverter. But in case of it is that inverter is operating in island, that time it is separated from the grid. So we don't know so suppose if we connected to the grid, the PLL measure the frequency, phase angle, and voltage, all these things. But in case of there is no grid, it is operating islanding mode, we have to provide the V reference and frequency and phase angle, all these things we have to provide. So this is the same diagram here. From next slide onwards, I will explain how we can design the PI controllers in inner voltage control loop. So applying KCL at three-phase AC filter, we can get equation 30. See here if we apply KCL, see IA equal to IFA minus ILA. See, so from simply, these are simple KCL equations. So From that equation 13 shows the KCL equations at the three-phase AC filter. And similarly, here also these IA, IB, all these things are in AC in nature. So we have to transform ABC to DQ. So equation 14 shows the uh, transformed equations. Then we will apply the Laplace transform. Then we will get equation 15. Similar to this design also almost similar to the current controller design only. Just equations are like this. And here also this ID reference and IQ reference are determined based on the control law. So here this equation 16 is very important, and the closed loop control of the transfer function is shown in equation 17. See, same here this red box shows the physical system dynamics, and this green box is the already closed loop voltage source converter current controls. Already we have um, what is that? We have decoupled the ID and IQ. Then we got simple single input, single output systems with the transfer function of 1 by 1 plus STI. So that whole control loop we are keeping here. Then again we are to get the desired output voltage. In islanding uh, operation, we need to give the voltage set points, voltage frequency. So here by using voltage controller, same here also, if you see this red box, here VSD is depending upon the VSQ. So here also there is coupling between the VSD and VSQ. So first we have to decouple, then only we can get the simple single input, single output systems. So this is also multi-input. Here the two inputs VSD and VSQ, and outputs are VSD and VSQ. So this is multi-input, multi-output system. So first we have to convert this multi-input, multi-output system into two single input, single output systems like previously what we have done. So in the current control loop also same what we have done. Similarly here also we are converting the multi-input, multi-output system into two single input, single output systems. And similarly here here also the compensators is just proportional. This is just not a PI controller, it is just simple P. This is a just proportional term we have considered just KV, because since the open loop system is already having one pole at the origin, so it is more than sufficient for the compensators to be pure proportional compensators. So PI compensators can also be chosen. So we can use here PI compensator also, but P compensator is sufficient because already we have one what is that one S is here. Okay, so this is sufficient to use one pole at origin. So that's why we can use directly one P compensator is sufficient. And from that finally the closed loop transfer function is shown in equation 4. So here the table 1 shows the traditional DQ frame controller. So here the grid or PCC voltage is 450 volts and system frequency. This table 1 shows the control parameters used in the simulation study. See, in figure 8, this is a simple DQ controlled inverter in standalone mode. The ABC result shows the standalone mode. In standalone mode, see, at 0.4 seconds, the load is changed from 1 kilowatt to some 1.5 kilowatt. So accordingly, see, if the current is changed at 0.4 seconds, okay, within 1 or 2 cycles, the current reaches the steady state value. Similarly, here see, you can see in the figure A, you can see the voltage dip. And at 0.6, the load is suddenly reduced. So there again, the voltage dip is we can observe. And in grid connected mode, see, so we are giving some reference active and reactive powers here. Actually, in the D is fixed. The D is not changing because this is PCC voltage. So it won't affect. But the real and reactive power what is that? The real and reactive power set points we are already set. Suppose in case of, if you see the figure E, the real power is initially up to 2 seconds is 0. 2 to 4 seconds the real power is 500 watt. So our inverter has to inject 500 watt into the grid. Okay, that's it. These are the results of the TQ control inverter in both standalone and grid connected mode. Yes, this limitation is actually we have, what we have done is just simply DQ frame control. This control strategy is not applicable for parallel inverter operation, because so if there is two inverters, this controller simply is giving some reference voltage only, but it how to share the power, this controller don't know. So we have to go some droop controller, some other what is that, advanced controller for parallel operation. So droop control is realized by simulating the already we know the droop characteristics of the generator in a traditional grid, and controlling the output voltage and frequency of the there accordingly. Based on the droop characteristics, we can get the voltage and frequency set points. Here also based on the what is that, based on the load, we will we will adjust the active and reactive power set points. So the benefits of droop control methods are simple and easy implementation, and reliable, high flexibility, and power ratings are different. We can consider different power ratings also. Okay, and this 2122 shows the relation between active power and frequency and reactive power and voltage. Here the F set, V set are the rated frequency and voltage set points, and real and reactive power set points is the P set and Q set, and M and N are the droop coefficients. So suppose if there is the actual power is more than the, what is the P set, the rated power, then the frequency definitely should reduce. So the F set is suppose is 50 minus M into P minus P set. So if the P is more than P set, definitely it is a sum total overall, that's M into P minus P set is negative value. Suppose definitely the frequency will dip if the actual power is more than is less than the rated power, then definitely the frequency will increase. The frequency will increase. So similarly, in case of reactive power, the voltage may vary, vice versa. And coming to droop control implementation. So previously, I already explained the current control loop and voltage control loop. And here the droop control is already I given some equations previously. So from the equation 21 and 22, we can implement. This is model simulation diagram. By using this model diagram, we can easily implement this whole system in MATLAB. Okay, and simulation results in standalone microgrid. Here the schematic of parallel inverter system is shown in figure 10. In this case, we have considered two inverters operated in parallel, and those two inverters operated in parallel and in standalone mode, not connected to the grid. And table 2 shows the control parameters used in the simulation study. Coming to the results, see. So here these two in droop controller, how the current sharing. The figure A shows the current sharing, and B is the terminal output voltage. And here the inverter 1 and inverter 2 synchronized properly, and C is the load current. And mainly from the figure shown in A, we can clearly understand that two inverters are not same rated. That's why they are generating different currents sharing, not equal sharing. It is unequal power sharing. And we have published this work in the IT, International Transactions on Electrical Energy Systems, in this journal we have published. Our team is published this work in this journal. This is Wheelie journal. And coming to the limitation in droop control, here main drawback is suppose there is sudden change in the load. So, so it is the immediately the frequency or voltage set point is changed suddenly. So sometimes the rate of change of frequency is high because if there is change in the active power, the frequency set point immediately will change. So what happens sometimes the relay may understand it is a fault. So that's why the frequency relay that is not depending upon the power. The frequency relay may think it is a fault. That is the drawback in case of droop control. If we go for virtual synchronous machine control, there is some virtual inertia. The frequency set point not suddenly change. It will change slowly. So then we can rectify this problem. Here, actually, what we have studied in our power systems, we have studied about only synchronous generators and synchronous machines, all those things. But we have not studied anything related to inverter-based power generation. So recently, in 2021, uh, the Peng et al. They published one paper, Droop Control Inverters as Educational Control Design Project in IEEE Transactions on Power Systems. They published one paper based on that. They are planning to add one chapter or one unit that is purely related to inverter based power generation and control of the inverter. How? So, from that paper, I have taken this figure 12. It is a detailed model of three-phase inverter with cascaded droop, voltage, and current control loops. Already, I have explained how to implement the droop control in MATLAB. So here also he is similar, but here see in his droop controller he considered see here f equal to f naught. This is what is that? This f naught is the 50 is fixed value, but this f is the uh, what is that set point, new set point. So here the f new is f naught minus kf into p measure. So actually the our equation is f equal to f naught minus m into some we have considered some m here he considered kf some m into p minus p set, but here kf into p measure. So here he considered p set is 0, q set is 0. That's why he designed that droop controller like this, and remaining all the things are same like as on what I have explained in my work. These people are also doing same thing, but the droop control in the droop controller, the set points different. That's it. Remaining everything is same. And you know how to design the current control loop and voltage control loop and this droop control. So then from this, I think from this lecture, all you can easily implement the droop control in MATLAB. This is simulation model of power measurement, okay, and droop controller. These are some references related to these slides. Okay, next I will go to some comparison of okay. Here I will compare the droop control results and virtual synchronous machine and virtual oscillator control for parallel inverter in standalone mode. So here this droop control is the basic control for grid forming inverters, okay, and compared the virtual synchronous machine is nothing but some little bit advancing in the droop control. Initially in the droop controller we have considered the equations just some f equal to f naught minus some m into p minus p set. So but in case of VSM we will consider the swing equations to reduce the rate of change of frequency. That is the little bit advancement between the droop control and VSM. And coming to the virtual oscillator control, this is virtual oscillator control is a it is a current what is a time dependent controller. So if there is, it is depending upon the what is that current, feedback current. But in case of droop and VSM, first we have to calculate the active and reactive powers. To calculate the active and reactive power, we have to use some filters. So these are not what is that time domain. These are our phasorial calculations we have done, and then we have applied all this control law. But in case of virtual oscillator control, it is a time domain control. If there is in the system, in the physical system, the current is changed, immediately the controller will act. So compared to droop and VSM, the virtual oscillator control transient response is very quick. Those these all those things I will shown in the later slides. In this chapter, I will try to cover group control, VSM, and VOC in standalone microgrid, and I will show some MATLAB comparative results, and I will show some experimentation by using VOC control. And coming to droop control, already droop control I have explained. Okay, this is the droop control implementation, and I have shown some results also. Now I am coming to virtual synchronous machine. This VSM is inspired by the same conventional synchronous machine. Both droop control and VSM control are inspired from the conventional synchronous machine, because this all already we have connected all our conventional synchronous machine connected to a grid, and we are operating properly. But the problem is, in future, if the renewable energy or inverter based resources are increasing day by day, one day what will happen? The domination of inverter based generation is increased. So at a particular time, the inverter based power or inverter based generation is more than the conventional power generation. Then the inertia is not sufficient to withstand the whole power system. Then there is a huge blackout. So that is the problem. That's why the researchers are working on this work. These inverters also uh, act like a synchronous machine. It means it is also will give some inertia. How the inertia came in synchronous machine? The rotor is there. It is uh, running with very fast, around 3000 RPM. So there some inertia is there. But in case of inverters, there is no rotating thing. There is no rotor, so there is no inertia is there. So we have to use some batteries or supercapacitors to immediately respond. So any what is that, any disturbance in the load side, those can immediately act, and it should mimic the synchronous machine dynamics. Then only we can in future we will make a safe grid. Otherwise it is very difficult to maintain the grid stability, because the inverters don't have any inertia. And the main concept of VSM control is to mimic the steady state as well transient properties of a synchronous machine on an inverter. So actually in droop controller, it will mimic only steady state only. But in case of transient case, I told you previously, there is a high rate of change of frequency. So the frequency relay may understand, may think it is a fault. That is the problem in case of transient. But by using inertia, virtual synchronous machine, we will get both steady state and transient properties of synchronous machine. And the three main inherent features of a synchronous machine are inertia, synchronous machine due to rotating masses, that is rotor, and damping effect due to damper windings. Not only rotor, we have damper windings in the our conventional synchronous machine. And speed droop characteristics of a synchronous generator for load sharing. These three are we have considered from the these are the inherent features of synchronous machine. But in case of VSM, we will consider system parameters can be varied. So in physical system, once our conventional synchronous machine is designed, We cannot vary anything. Everything is fixed. The system parameters not vary. But in case of we implement those all the properties in microcontrollers, we can easily change the code and we can easily change the parameters. That is the extra benefit with VSM. And system parameters can be chosen upon the application, which are not which is impossible with synchronous machine. In synchronous machine, that is fixed. Whatever it want to give, it want to inject the power into the grid, it will give. That's it. But in case of VSM, we can vary all these parameters and somewhat. So these are the key extra benefits compared to a synchronous machine. And here the equation 6.3 is our conventional inertia equations, and 6.4 is shows the damping equations, and 6.5 shows the our governor model, and we are clubbing all the 6.3, 6.4, 6.5 to get the final what is that final equation. So by using this equation 6.6, we can in the I will show the implementation portion. There you can understand this 6.6 important. See here the swing equation. The whole equation 6.6 we are implementing in this box in this swing equation, and remaining all the C. Here the group controller is same, and the voltage control loop is there, the current control loop is there. The main problem is frequency. So there by using swing equation, the rate of change of frequency we can reduce. And I will show the comparison between group and VSM. The same system. Now I am applying VSM control, and these are the VSM control results. It is also similarly droop control. The main difference is, see here, the comparison between droop and VSM. Here, the drawback associated with droop control is high rate of change of frequency. So see, here the magenta color is high rate of change of frequency change. Suddenly dip is there. But in blue color, the rate of change of frequency is reduced. Okay. That is the main advantage of VSM compared to droop control. Okay, but still some limitations in the droop and VSM. Those are the droop and VSM control requires low pass filters for active and reactive power calculation. This has some negative impact on the transient response. But VOC is a time domain controller. There no need to calculate any active and reactive power. Only the based on the feedback current only the controller act accordingly. So then we can eliminate these low pass filters. So the what is that? The transient response may be improved in the VOC. Coming to VOC implementation. The VOC implementation, this is three-phase VOC implementation. Here I am not going into detailed explanation, because in the next unit I will explain clearly about what is VOC. All those things I will explain. Just here I am showing some results by using VOC. In the next unit or next slides, I will explain the what is VOC and how we can, what is the philosophy of the VOC and how we are going to implement this VOC in simulation and hardware platforms. Okay. Here I will, this is the just implementation of VOC, the same system I'm considered, and these are the results. And this is the frequency comparison. Okay. And these are the active power tracking. So overall, compared to all results, the VOC has showed some better results. And what is VOC, all these things I will explain in the later slides. And coming to experimentation, so we have some limited resources. So the three-phase inverters connected in parallel and operating is little bit difficult. But what we have done is we have just considered one three-phase inverter. See, we have one semicron inverter stack. This whole thing from this RYB2 up to this filter, this is one semicron inverter stack. There one three-phase diode bridge rectifier is there. If we give some three-phase AC supply directly, we will get some DC link. Here one DC link capacitor is there. Here we will get some what is that required DC voltage we will get, because we will use three-phase variac. So from the three-phase variac we will give some RYB. We will not apply 450 directly between R and Y. We will give some 100 or 200 to what is that, slowly we will vary that three-phase variac knob to get the required DC supply. Okay, here I want just 260 volts DC supply. So I think in the three-phase variac, the line-to-line voltage the 100 is sufficient to get the 260 volts in DC side. Okay, so we have DC supply, we have one three-phase inverter, and we have designed a LC filter. Okay, then how to implement in hardware? So if we have one semicron inverter stack is sufficient to implement this hardware setup. Then we have to design LF and CF. In my lab, we have designed one 6 millihenry inductor and 36 microfarad capacitor. We have directly ordered, and you can order this filter, filter and filter capacitor, filter inductor. We can, what is that? We can order in online. First, we have to design this how much values we need LF and CF. Accordingly, then we have to purchase. So if you purchase LF and CF, accordingly we will design the system. Okay. So then we have considered one balanced load, and here actually this VOC works on that current feedback signal only. So here I have used one current sensor LA55P. It works on the Hall effect. It is a Hall effect sensor. So it is taking the, what is that? It is taking the live current, but it is giving some signal. That's why it is Hall effect. If it is giving physical signal and it is giving some physical current, then it is like a transformer. But it is directly taking the live current. It is connected in series, but it is giving some signal level. That current signal we are giving to the OPLRT or our VOC control. I have used OPLRT. It is a real-time simulator. First, I have to explain about what is OPLRT. OPLRT is one type of controller. Not only controller. In OPLRT, we can study the system. Actually, what is the difference between MATLAB and OPLRT? MATLAB is a software in which we can approximate. Okay, once we have studied in MATLAB, okay, we can implement this in real time, but we don't know exactly. Once we have run in the MATLAB, we cannot directly go to the physical system. Before that, if you run that system in OPLRT, then we will get more confidence if once our MATLAB model is running in the OPLRT. Okay, then so we can understand, we will get some more confidence. Okay, we can operate this system in physically also. So that is the OPLRT. But here that OPLRT I am used as, okay, listen. Here here I have used the OPLRT as a just simple controller. Okay, this controller is nothing but VOC. In the OPLRT, I have dumped the dynamics of the VOC. Okay, so and this is the OPLRT having some analog input and some PWM out. So for inverter control, we need pulse width modulation signals, and the feedback is current. So for injecting the current into the OPLRT, we need analog inputs. So the OPLRT having some 16 or 32 analog inputs. So, but in my case, just one analog in is sufficient. I am just connected this current signal or current feedback in analog input. Then the OPLRT is give some PWM signals. So here I have used this 6N135 is nothing but isolator. Okay, so if any what is the circulating current, anything happen, this isolator will isolate my OPLRT and my physical system. Otherwise my OPLRT is very costly setup. If any it is damaged, it is huge loss. That's why I have used some opto isolators like 6N135 to isolate the my system and my controller. Okay, and later I have used some NOT gates and level shifters to get the desired what is that? I actually that semicron inverter stack need the 15 volts pulse. It needs signal, but the signal magnitude should be minimum 15 volts. That's why, see, here actually the total six switches are there, but S1 uh, at a time two switches is on. So see, suppose the S1 is on, the S4 should be off. Otherwise, there is a shoot through fault. There is dead short circuit across the DC bus or DC supply. Then the two switches will be burned. That is shoot through fault. So we have to take care about S1 and S4. If the S1 is on, we have to uh, switch off the S4. That's why I have used NOT gate. That's why I'm generating only three signals. Suppose one signal is giving to S1 means the other signal I know. The S1 is on means S4 is off. Okay. See, if you see the signal, I'm using some NOT gates. So if suppose I'm generating S1, S3, S5, by using NOT gate, I will get the S4, S2, S6. Okay. That's why I'm used one NOT gate and one level shifter. Okay. So if you have the three more opto isolators, the same inverted pulses you can get from Opalati also. Opalati can give up to some 16 or 32 signals, PW out signals. Okay, but here I used NOT gate and I have used CD4504 is nothing but level shifter. Here actually the Opalati will give 5 volts only. Okay, but the CD4504 will shift that 5 volts to 15 volts. Okay, why? Our semicron inverter will take only 15 volts supply only. The magnitude of the pulse should be 15 volts. Otherwise, the switch will not turn on. Okay, and the gate drivers, all those things are readily available in the semicron inverter. Okay, so if you have a semicron stack and if you have one, not only Opalati is very costly setup, if you have some microcontroller, then these filters and these level shifters, all these things are very cheap, you can purchase easily. So if you have one semicron inverter and one microcontroller, you can easily implement this whole setup in your lab. And this figure 6.14 shows the experimental setup picture. See here, this is three-phase inverter stack. Okay, and this DC power supply, this DC power supply for these level shifter and NOT gates required some DC power supply. And similarly, Opalati also requires some 5 volts DC supply. Okay, and our current sensor requires. Here I have used LA55PC. This is the top view of my current sensor. That current sensor also required plus or minus 15 voltage supply. Okay, for that you need to design plus or minus 15 voltage supply. Okay, and I have used some three-phase resistive load bank, which is readily available in our lab actually. And this is a three-phase auto transformer or three-phase variac to set my DC supply to the inverter. Okay, and just by the figure 6.15 shows the dynamic response of voltage and phase current of one phase current I am showing and one line to line voltage. Okay, and I have at after some time I am giving some disturbance, I am changing the low, that immediately the current is, see here the current is changed immediately. Okay, this is and this work is published in protection and control of modern power systems. Okay, this is a high impact factor journal. Our team has published this work in PCMP journal. And coming to conclusions, and Root, VSM and VOC control strategies are implemented in standalone microgrid. The VOC, the synchronization condition. In VOC, the synchronization condition is independent of load parameters and number of inverters. and we have presented MATLAB and Simulink results. Okay, and I have shown some experimental results also of the VOC control. Okay, and next I'm going to some other slides. Actually, I have not explained about what is VOC, how to implement the VOC. The next slides I will explain about VOC. So in this unit, first I will explain about what is VOC. Then the VOC is existed. We have apply some optimization methods to find the VOC parameters, and we have published this work in one of the reputed journal that I will show you. All those results I will show you in this chapter. Yes, coming to VOC. The VOC is a decentralized control strategy for islanded microgrids where inverters are regulated to emulate the dynamics of nonlinear oscillators. Actually, initially the Droop and VSM trying to mimic the synchronous machine dynamics. Similarly, this VOC is the dynamics of nonlinear oscillators. So that is a mathematical concept. From that we have inspired and we have considered some dynamics from the nonlinear oscillators, and we have those dynamics we are applying in the microcontroller to control our inverter. And this VOC regulates the amplitude and frequency of the inverter terminal voltage. Consequently, the inverter synchronize their voltage outputs and share the load power in proportion in their power ratings. Okay, the VOC regulates the inverter terminal voltage, and it is automatically synchronizes, okay, that the nonlinear oscillators. So those oscillators automatically synchronize. Okay, so why it is automatically synchronized? For that, one theorem is there in mathematical point of view. One linear theorem is there. If any second order differential equation satisfies those dynamic satisfies the theorem, then it will give some stable limit cycle. Whatever the initial values, finally it will reaches that that particular limit cycle only. Okay, and the VOC works on the, I told you already previously, it works on the only current feedback signals and does not require any real and reactive power calculations and explicit frequency and voltage amplitude commands. So in case of our Droop control and VSM controller, we have calculated active and reactive powers. Then we have some, what is that? We have some Droop equations or VSM equations. Then we have some current control loop, voltage control loop. So all these things we have. And we are giving some voltage and frequency set points. But in case of VOC, all these things are not required. And the synchronization condition also. So for to synchronize the parallel inverters, we need some synchronization condition. Okay, so which is independent of the load parameter. Okay, the synchronization condition of the inverters which are controlled by VOC is not depending upon the load parameters, and number of inverters are participating in the system. Suppose I have two inverters in parallel. So if I consider 10 inverters also, no issue. The synchronization condition is independent of the load parameters and number of inverters are participated in the system. So from this, what we can understand is we can connect n number of inverters in the system. Okay, first, what is Lienard theorem and what is Lienard oscillator actually? So the figure 2.1 shows the electrical schematic of Lienard oscillator and its waveforms. So if we apply KCL and KVL, finally we will get a second order, okay, second order differential equations, because we have two, one L and one C. So definitely we will get second order differential equations only. See, If the initial conditions, suppose the consider a non-linear second order ordinary differential system, suppose that is shown in equation 2.1, where x is the real valued function and f of x and g of x are the real and differentiable, and f of x should be even and g of x should be odd function respectively. And in figure 2.2 shows some function capital F of x. The system in equation 2.1 has a unique and stable limit cycle. See here, one green circle is there. This is nothing but uh, unique stable limit cycle. If the IL and VC having different initial conditions, still after some time, it will give sustained oscillations. Okay, with constant magnitude, unique stable limit cycle. Okay, so that unit stable limit cycle we will use as a control signal in our control, in our inverter controller. Okay, see what is Linear theorem. So if the g of x is greater than 0 for all x greater than 0, and the capital F of x has exactly one positive root, that is p, and f of x is less than 0 when uh, the x is in between 0 and p. Okay, and the f of x is monotonically increases for x greater than p. Okay, so these four conditions, the equation 2.1 satisfies these four conditions, then only it will give a unique stable limit cycle. That limit cycle will act like a our modulating signal in the inverter control. Okay, so here the concept is the main thing. The all this VOC concept is coming from the strong mathematical background. Okay, from that dynamics only, the only we are simply considering. Once we are satisfying our dynamics, satisfying the Linear theorem, then our dynamics will give a proper stable limit cycle. Okay, okay, coming to virtual oscillator. The construction of dead zone oscillator is inspired by the well-known Van der Pol oscillator. This Van der Pol oscillator, all these are mathematical concepts, and the linear subsystem of oscillator is passive RLC circuit. See, the figure 2.2 shows the electrical schematic of the dead zone oscillator. This oscillator having two subsystems. One is this linear subsystem, that is RLC, passive RLC circuit, and another one is C, non-linear voltage dependent current source. Here the G of V is nothing but current. Okay, the G of V is depending upon the V, so that's why this is called voltage dependent. Okay, non-linear voltage dependent current source. Okay, that G of V is nothing but f of V minus sigma V, where f of V is the dead zone function. That's why we call it as a dead zone oscillator. Okay, see, in figure 3.2a, the dead zone characteristics are shown in figure 3.2a, 2.3a. So we have modified the dead zone characteristics into C in figure 2.3b, non-linear voltage dependent current source. Actually, there is no dead zone in the what is that non-linear voltage dependent current source, but which is inspired by the dead zone characteristics. That's why we call it as a dead zone oscillator. Okay, so this figure 2.2, if we apply KCL and KVL, we have two storage elements, L and C. Finally, we will get second order differential equations, that is shown in equation 2.4. Okay, these differential equations satisfies the Linear theorem. So this 2.4 satisfies the Linear theorem. Okay, then we will get unique stable limit cycle. Okay, and coming to the design and parameter selection of DZO based VOC. So here the reference 13. Actually, this VOC is patented by the Professor Brian B. Jansen. He is an American scientist. He invented this VOC. Actually, the VOC dynamics are there in mathematical concepts. He what is that? He published some patents on this VOC. He applied those mathematical concepts to the parallel inverters. Okay, and he have published several IEEE transactions. And from this reference, you can easily design the parameters of DZO. Okay, and now coming to implementation. So the figure 2.4 shows the schematic implementation of DZO based VOC. So the implementation is very simple because in the digital controller, this is nothing but suppose in case of what is that? We got some second order differential equations. So in MATLAB, you will consider a embedded MATLAB function. Okay, in that function, you will write the all the dynamics. Okay, and this physical system you can easily implement in the MATLAB. The main thing is the problem is controller. The controller only this controller is a there is actually why we call it as a virtual oscillator control. The problem is if you observe the C values and inductor values, those values are looking very odd actually. In what we can in the code only we can write, but practically those capacitor if you design a capacitor based on that value, it is a very big. It is one room size, one building size. Okay, that's why the values are not physically implementable. That's why we call it as a virtual oscillator control. So we are saying that capacitor value is some big value, but that is not physically exist. But we are simply saying because we are writing some dynamics in the microcontroller. This is not physically present. That's why we call it as virtual. Okay, and those dynamics we are implementing in the embedded MATLAB function, and we have considered that load current, and we will give it to the embedded function, that is as a what is that feedback, and that what is that from that MATLAB embedded function, it will give some VC1. Then we will use some voltage gain and 1 by VDC. All these are the this is 1 by VDC is nothing but the converter gain. Okay, we will consider by using 1 by VDC. Actually in physical system it will give some gain. That gain we are what is that? By multiplying this 1 by VDC, it will be neutralized. Finally, we are generating modulating signal. By using modulating signal, we can generate the pulses to the inverter. And in this work, we have considered normal different types of optimization methods. We have considered particle swarm optimization and sine cosine algorithm, optimization algorithm, and modified sine cosine algorithm. Some artificial what is that African vulture optimization algorithm. So we have used some different optimization algorithms to what is that to design these parameters. That is the little bit novelty in my work to publish. So this work is coming to the simulation results. Here I have considered two single phase inverters and operated in parallel. And here the table 2.1 shows the system and control parameters, and conventional VOC parameters are there. And by using by using different optimization methods, I have consider I got some different values from the optimization algorithms of the VOC parameter. So here I have considered some of the VOC parameters I have designed by using the optimization methods, and I have applied those values into my system, and I will observe, we will see the results, what happened. So almost from these results, we can see the initial response is very good in my optimization methods. And this work is published in ISA transaction, which is a elsewhere journal, and our team published this work in this journal. And I will directly show the comparative results. All if we see the results individually, it almost all are looking same. If we see the startup response and THD, see, and there is a trade-off between the initial response and THD. If the initial response is fast, but the system having little bit more harmonics. Okay, if the system response is sluggish, okay, then the THD is good. So it is a typical trade-off. If you want good quality and if you don't want a fast response, then you can go to the one method. If you want fast response, okay, and little bit compromising THD, okay, then you will get mm, but you can use some other method. Okay. And coming to the, see here, the active power tracking. From that active power tracking, in the artificial jellyfish stretch optimization, by using that optimization I got faster response. The table 2.2 shows the some comparative study of classical VOC and different optimized VOCs and the experimental results. So here I have considered, this is a single phase system. That's why I have considered two inverters and operated in parallel. So Arnab sir told me to more stress on the hardware experimentation. Now I'm trying to explain each and every point in my experimental setup. Okay. So then from this lecture, anyone can easily implement their hardware setup in the point of inverters. Okay. So in my case I have considered two inverters. Okay, see, this is the single phase inverter with gate drivers, and this is the another. Okay, this is the another inverter. Okay, so I have considered two inverters. See, here also I have used one semicron inverter stack. Actually, semicron inverter stack having four legs. Okay, but one I have considered two legs as one inverter and another two legs as another inverter. Okay, and I am giving the same DC supply to the both the inverters. That is my assumptions actually. In due to what is that? I have only one inverter stack only. So I have to with my limited resources anyway I have to complete my hardware setup. So what I have done, in my case I have considered that four in the out of four stacks I have considered two stacks as one single phase inverter and another two uh, what is that, two legs, another two legs considered as a another inverter. Okay, and already I explained in the previous slides how to get the DC link voltage. In the semicron inverter stack, there is one three-phase diode bridge rectifier, and by using the three-phase variac, we will define this DC voltage. So whatever, how much DC supply you want, you can by using three-phase variac, you will get. Okay, and see, similarly, is a single phase. Previously, I have explained that there I have considered three-phase filter. It is single phase system. That's why I have considered single phase filter LF and CF. First, we have to design the filter and we have order in the online. And this current transducer, this is nothing but LA55P. This is current sensor. We can order from the online. Okay, and the sensor calibration also, if possible, if time permits, I will explain the how to calibrate the LA55P. Okay. And I have used this current sensor. It is a hall effect sensor. Okay, this is simply sense the load current. Okay, see here also another inverter, here also another current sensor. So what it will do in the VOC control is a current, it works on the current feedback signal only. Okay, in the OPLRT I have two controllers. The OPLRT actually, in the OPLRT we can run uh, in microcontroller we have to use two microcontrollers, but the advantage in OPLRT we can consider n number of controllers parallelly, because the OPLRT is the uh, very advanced tool, and this is not made for it is not a, it will not be used for a microcontroller. Job is very small job for OPLRT. The OPLRT can run the whole physical system. Okay, that's why the if we have OPLRT, that is my greatest advantage. That's why I have easily complete my hardware setup. In the OPLRT, I have considered two control loops. Okay, two controllers. One is one controller, one VOC controller for inverter 1 and another VOC controller for inverter 2. Okay, for one inverter control, I will give one here. I will consider two analog inputs. One analog input for one VOC1 and another analog input to the VOC2. Okay. Similarly, see here S1, S3, S2, S4. See, if I have one pulse is sufficient, okay, to get the four pulses. Why? Because this S1 and S4 operate at a time. Then only there is a closed path is there. Okay, then only current will flow. So if I generate one pulse is sufficient to control the one inverter, because S1 and S4 is same and S1 and S2 are the opposite. Okay, so inverted. So the S1 and S2 should not be short circuited at a time, because it is going to be a dead short circuit across the DC supply. So we have to eliminate. So we have to if the S1 is on, the S2 should be off. So that's why I have used NOT gate. Okay, so one pulse is sufficient to one pulse. Okay, one pulse is sufficient, and one NOT gate is required. Okay, and one level shifter, that is sufficient. And no need to, if you have semicron inverter stack, no need to design any gate drivers. Okay, by default gate drivers are there for all these 8 switches. Okay, 4 gate drivers are there. Each gate driver will generate 2 signals. Okay, for each leg, two two switches is nothing but one leg. For each leg, one gate driver is there in semicron inverter stack. The semicron inverter stack is costly, but some other vendors also making the duplicate version of the semicron inverter. Within 1 lakh or around 70,000, you can purchase that type of stacks. If you want, you can contact me. I will share some vendors details. Okay. So if you have one inverter stack, then you can simply perform the single phase inverter. Two single phase inverters can operate in parallel by using one inverter stack. And already previous slides I have explained why isolator is opto isolator is required. If any circulating currents, I have to save my OPLRT controller. It is very costly. That's why I'm using an opto isolator. It will, if anything happens, it will isolate the physical system and my signal level system. So that's why the 6N135 is the opto isolator. And here I am used some buffer also. Sometimes what happens, there is some loading effect is there. The microcontroller, actually the OPLRT will give 5 volts signal. Sometimes what will happen, due to this opto isolators are not gates, some loading effect, it will give some 2.5 volts, 2 volts signal. That is not sufficient to that is not sufficient for this opto isolator or gate or not gate or level shifter. So what this 6N SN74 LS125, this LS125 is nothing but a buffer. It will eliminate that loading effect. Okay, if anything it will remove that loading effect. It will give the 5 volt signal to the opto isolator. Then opto isolator is isolates our physical system and our OPLRT, and that opto isolator is nothing but it will send the same signal only. Okay, but it will send some inverted signal. Okay, if you see, okay, if the diode is off, it will give 5 volt supply. So it is a I think if you go through the 6N135 manual, you can clearly understand how it will operate. Okay, but it will give the, if I give 5 volts, it will give finally 5 volts magnitude signal. and then it will go through the NOT gate, because I'm generating only one signal from the O polarity for one inverter and another PWM signal for another inverter. From that one signal only, I'm actually for single phase inverter we need two PWM signals. For S1 and S4 one signal is required, and S2 and S3 one signal is required. But um, luckily that S1 and S2 are the same leg, so by using NOT gate we can generate the S2. Okay, so here in this case the O polarity generates two PWM outputs for two inverter. From the two PWM output we can generate the what is that, the required signals by using NOT gate. And level shifter, already I told you the level shifter is required. Our semicron inverter stack requires the 15 volt supply. Okay, the 15 volts magnitude pulse only, otherwise it cannot take. That's why we are shifting the 5 volts signals to the 15 volt signal. Okay, and this 50 C, if you see the CD450 level shifter, it requires one 5 volt supply and one 15 volt supply. Similarly, this NOT gate also required one 5 volt supply. We have to give 5 volt supply across the pin 14 and pin 7. Okay, if you go through the what is that, the pin diagram or the manual of this gate, you can clearly understand that what is inside the gate and what is happening. But simply you can remember, yeah, in NOT gate you have to apply 5 volts across 14 and 7. Okay, NOT gate, suppose if the input is 13, the output is 12. Okay, if 5 volt pulse is there, the 12 will give the, what is that, the inverted pulse it will give. Okay, similarly the 11 is one input, the 10 is the output, 9 is input, 8 is the output. Similarly in case of level shifter also, we have to apply 5 volts across 1 and 8. 8 is the ground. Similarly we have to apply 15 volts across 16, pin 16 and 8. Okay, so we have to apply for supply, then only the IC will work. Okay, and the see here, the 3 is the input, 2 is the output. Okay, if you apply input at 5, we are giving the 5 volt magnitude pulse at pin 5, at the output pin 4 will give the 15 volts pulse. That's it. It is simply shift, level shift. Okay, shifts the level of the control pulse. I think from this slide you can easily implement the hardware of the two single phase parallel inverters. Okay, but for that the basic requirements are at least one semicron inverter stack or the duplicate version of the inverter stack, and two single phase filters and one common load, and we need O polarity. If you have some C2000 microcontroller, so you will use two microcontrollers. Okay, and the remaining all are same. That's it. If you show the figure 2.16 is the experimental setup picture, and table 2.3 shows the parameters of the system, both parameter and control parameters of the experimental study. And these are the some results. And this work is published on the published in ISA transactions. And so this is the comparison. If you
Hello, sir.
Okay, okay. Tell
Hello,
me. Hello.
sir, can you go to previous slide?
Slide number 18.
Previous, that hardware setup you have shown me.
Okay, hardware. Okay, okay. Tell me 15. Okay,
Yeah,
tell
yeah.
me.
Sir,
Tell me, sir.
this OpenRT, that inside, what drop controller or VOC control, what we have implemented?
I have implemented here VOC controllers. Only VOC.
Oh, only VOC. And
VOC.
how to do that thing?
Sir, Opalati is directly we can dump our MATLAB into Opalati. So that is the biggest advantage.
That all that that model based thing you have developed in the MATLAB, and those things you have dumped into the Opalati.
Yes, yes. Yeah? Only the controller model. Yes, actually, I'm getting one. See, here one current sensor is there. It will give some feedback current. The VOC works on the current feedback signal. Okay. The
Okay, sir.
OPLAT having some analog inputs.
Correct.
Okay. So
Hmm.
I'm here. We have two inverters. These two inverters controllers works on the only current feedback signals. So that's why I have considered two current sensors. Okay. This is one
Okay.
current sensor and this is another current sensor.
Correct.
So for me, two analog inputs are sufficient. So what happened in OPLAT? Once we are giving the supply to the analog input, directly our MATLAB model is there. I told you how to apply
Yeah.
VOC. We have considered one embedded MATLAB function. Okay. In that
Mm-hmm.
function, you can write the simply the second order differential equation. Simply.
Mm-hmm. Mm-hmm.
Okay. There already our I in the dynamics, IOSC is there. IOSC is nothing but the feedback current. There
Mm.
you can directly give this analog into that block directly.
Okay.
So if you actually in real time, if you show, if possible, if I have another lecture definitely I will show some. I will take some screenshot what I have done. Actually, my
Mm-hmm.
laptop is some issue. That's why I am unable to add some slides. Okay. If I add
Okay.
some two, three more slides, if I take some screenshot of what I have done in my system, then you can clearly understand actually. If I'm unable to explain here, I'm just simply showing some opality. If you have some little
Okay.
bit idea of opality, then you can clearly understand. If you are
Mm-hmm.
new to opality, it is very
Yeah. Yeah.
difficult to
Correct.
understand. Okay, if
This is a
possible, you can take my
real-time
contact number
simulator,
from
sir.
Arnab sir.
Uh-huh.
Personally, I will show you. If I don't have any other lecture, so I
Okay.
will show you
Okay.
personally. Okay, some
Okay,
results of
sir.
this.
Okay, sir. No issue. And one more thing, this is a
Tell.
real-time simulator. What is the difference between that?
Actually, the opality is if you done something in your MATLAB,
Mm-hmm.
can you implement the same thing in real time?
Mm,
We don't know exactly. We are taking some variable step. It won't
mm,
possible to implement in real time. If it is fixed step, somewhat we can implement
okay.
in real time. So once our system run in
Mm-hmm.
opality,
Mm-hmm.
almost 99% we can able to run our system physically. It is the
Okay.
middle step. You are running some system in MATLAB. Okay,
Mm-hmm.
then you are directly go to the physical system. In between, if you have opality, you can verify your system whether you can run in physical or not. That is the main advantage of opality.
Okay. Okay. Thank you, sir.
Not
And one more thing.
99%. Huh,
Mm,
tell me.
mm. Continue. Continue, sir. And
Actually,
what?
in power system, people they have grid, they have 100 bus system, 200 bus system. For them, it is very difficult to take the system in real time. Na?
Correct.
That's why
Correct.
they will consider the whole real-time system in opality and they will use
Okay.
some controllers outside. Okay.
Okay,
In
sir.
my
Okay.
system is outside. Controller is
Mm-hmm.
opality. But in
Correct.
some cases, opality is system. You can consider
Oh, oh.
5 inverters in opality. You can take
Okay.
outside 5 microcontrollers.
Okay. Okay. Understood.
Okay,
Mm-hmm.
na?
Thank
So
you.
that
And
is
one
the
more.
biggest
Mm.
tell me.
And this IN74LS50N
Yeah,
50
that is not gate.
S04N.
Not
What is this, sir?
that is not gate, sir. That is not gate.
Only not yet. Okay.
Okay, I told you already. If the S1
Mhm.
and S2 is at short circuit at a time, what will happen? They
Understood.
will
Understood.
shoot through fault. Okay,
Correct.
the
Correct.
S1
Mhm.
signal I have, I am just simply inverted.
Yeah. Yeah.
Okay,
Understood. Understood.
yeah.
Okay. Thank you, sir. Thank you.
Okay, thank you. Shall I continue?
Yes.
Sir, one more
Continue.
doubt,
Tell.
yeah. So the like dead time between S1 and S2, it was taken by the semicron inverter or
Yes.
how we
That
are
is
maintaining
we
that
take
time?
care by semicron inverter. Otherwise, we have to make a circuit that is some I forgot that name. We have to make a one more circuit to give some gap.
Okay.
Definitely. Mm. That is will be take care by the semi. That's why if you have one semicron inverter stack or some duplicate version of stack, you can easily work on the inverters. Okay. Otherwise, it is difficult to design these gate drivers, and that is the blanking circuit. I think those circuits is a little bit difficult actually. If you make some circuits also, it will not work that much efficiently compared to semicron gate drivers. Okay.
Okay. Yeah. Thank you.
Okay. And these are the some of the results. I have see in figure 2.23. I have compared the initial response. Okay. So in some cases the initial response is fast, some cases initial response is late. So it is a trade-off. If we want fast initial response, you can take what is that? You can take fast controller. If you want a slow response and if you want good THT, then you can take some other optimized method. So we in this paper we have presented several optimization methods and we have shown different ways, different types of what is that fast response and THT trade-off we have shown, and accordingly we can consider the, and these are the conclusions of this paper actually.
Sir, is there any results like showing converting from like a grid to directly to the load? Like so now two inverters are running on the grid and shifting to load dynamically. Like then
Yeah,
how the response is there?
actually, in, uh, I have worked on the only just islanding mode only. I have considered two inverter, which is not connected to the grid. Hello.
Yes, yes. So, but
So there is
the control system which was developed over here is like can be run on the like a grid mode and islanding mode, both modes.
only
Is it
islanding mode. I am giving some load disturbance. See here in this result. See the current is changing now. The voltage is fixed, but the current
okay?
is changed. After some time, I am changing the load. Okay. So in physical system is very difficult to develop in grid connected all those things. We have some limited facilities. Based on the facilities only, I am considered just two inverters and one simple load, and I am varying the load and how my controller response is, how my controller is acting on the system. That I have studied. That's it.
Okay,
Okay.
but
It is
VOC can be implemented. Means like the method control method can be implemented for the grid and off grid inverters. Both the things.
yes, yes. Some recently some papers published on. Initially, it was for islanded only.
Mm-hmm.
After some modifications, it is we can connect to grid also. Some papers are there. Okay, you can search. You
Okay.
will get some papers grid connected VOC controlled inverters.
So as for
I,
you, which one is the best, sir? Like for the grid and off grid. So which control
uh,
method will be the best one for the both the means like if you want to inverter want to run in the both the modes simultaneously and paralleling option should be there. Which has to
okay,
be like chosen.
okay. From my understanding, actually in grid connected mode, suppose in present our power system already dominated by the synchronous missions. So grid connected is very easy. All our inverters are directly connected to the grid. If there is grid is on, it will inject some active and reactive power into the grid. If there is no grid, it will sit ideal. It will not do anything, these inverters. But our idea is in future the renewable energy sources are increasing day by day. One day we will dominate the synchronous what is that? Synchronous generators. That day the new power system will emerge. So these VOCs are now not fully what is that full not fully designed actually. People are working after some 30-40 years. What will happen? The renewable energy sources will dominate the conventional synchronous machines. So then how we are stabilize our power systems? So these VOCs we cannot implement actually nowadays. We are just simply just studying. After 20-30 years, if the more researchers work on these all these methods, if then it will become more powerful, then we can form only grid forming inverters. Grid forming inverters means only our inverter will make a grid. Like nowadays, our synchronous machines are making a grid actually. But in future, what will happen? All our inverters will make a grid. Okay, these
Okay.
controllers are not sufficient now, but in future the plan is like that. We have to make a grid by using inverter. That's why the topic is grid forming inverters.
Okay.
Actually, I don't have time. Actually, I have some slides if possible. If Arnab sir will give some another lecture or another session, definitely I will explain some machine learning based or artificial intelligence based VOC controller. That work we have published in IEEE transactions in power electronics. That work I will explain later if possible. If you have any queries, you can ask me. My session is completed. I have time up to 1. This 10 minutes for queries. If you have any doubts, you can ask me.
Hi, sir. Thank you for a very nice presentation and provided so many insights of various technologies. My query is that, like a droop control power-based method,
Okay.
am I audible?
Yes, you are audible. Absolutely audible.
Yeah.
Tell me. Tell me.
So droop control method, there are some research investigation in another direction, like validation of small signal stability and that limitation, like how much will be the droop allowed or gain values or tuning. Could you please highlight and in another direction, like a virtual synchronous or VOC, can we,
Yes.
is there any research can be further extended in the direction of analyzing small signal stability, or what is it already investigated and there will not be any concerns on the stability validation perspective, whether it could be in islanded mode or grid connected mode? Could you please provide your comments?
Sure, sure, sure. Actually, you are asking about any future scope of this work. Actually,
Yes,
this
in the
is
direction
this
of
is
linear
actually
analysis, small signal
what
stability.
we have
Yeah.
discussed is just primary level of the grid forming inverters. So
Mm.
you can work on the what is that actually protection. Already our protection systems are there for synchronous machine, but the same protection system will not be sufficient for inverter based grid forming inverters. Okay, so in that aspect you can if you are power system background, so you will read some research articles regarding grid forming inverters protection. If you
Mm.
are if you are control systems background, you can what is that this small signal analysis stability.
Okay.
Okay, so if you
Okay.
are power electronics based, you can design the efficiency of the switch. In the power electronic point of view, you can go through that way. So we have several options, and if you have some, you can apply model prediction control based VOC, some artificial intelligence and machine learning based approaches also you can use.
Okay. Okay. So still there will be a chance to investigate. The reason especially I would like to know is that there are even like grid following method or group control have some limitations where
Yeah,
the time we talk about it will have a stability issues. I
yeah, yeah.
understood that still some validation is needed in the direction for
Yes, yes,
grid
yes.
forming. Okay, thank you.
Okay, thank you, thank you.
Hello, sir.
Hello.
Yeah, may I ask one more question? Like in existing like hybrid inverters, like solar hybrid inverters, maybe those are also can be connected in parallel. So how which control method they are following? Do you have any insight on that one? Like
Okay, okay. You can tell me about your system. Hybrid means you have some DC bus, na?
yeah, yeah, hybrid system and like a
Okay, hybrid system. You have one DC bus and you have one inverter connected to it. Similarly, the same another system is there. You have to connect these two inverters parallelly. That is your
yeah,
idea.
yes, yes.
Yeah, yeah, yeah. You can connect, but actually you have to use some other controllers that will maintain the DC bus voltage. These inverters can maintain the output voltage frequency set points only. Okay, but the DC bus voltage you cannot control by using VOC. For that, you have to use some other controller to maintain the DC bus voltage. If you maintain the DC bus voltage properly, definitely you can connect all these inverters in parallel. No issue. and you have to do the some power management also.
Yeah.
Okay, na?
Yes, means like yeah, I will like try to write a mail to you. So means like I'm working on this type of paralleling of inverters and all.
Sure,
So
sure. You can take
yeah,
my contact details from Arnab Ghosh, sir. He will provide all the resource person contact numbers. You can mail
okay.
me. Okay, no issue. I will help you
Thank
out.
you very much, sir. Yeah,
Okay, thank you, sir. Okay, thank you.
yeah.
Shall we close this session? I think Arnab sir may be busy. I will actually I would like to thank Professor Arnab Ghosh sir. Arnab Ghosh sir is very sincere and hardworking professor. He is my supervisor. He was my PhD supervisor. He is young and energetic professor. I have learned so many things from Professor Arnab Ghosh, sir. I think yesterday you observed at night 12 o'clock, he arranged a test meeting and he is that much dedicated. He's having family, he's having small child. Still, he is that much passionate about conducting all these workshops and delivering these sessions. Uh, so all we are learn so many things from Professor Arnab Ghosh, sir. I'm very happy to have this kind of professor in my PhD journey. And okay, thank you, Arnab sir, to giving this opportunity. I think he's not in the meeting. I think he may be in some other meeting. So this is lunch time. From 1 to 3, you have lunch time, and again 3 another session will start. Okay. So if you for lunch you may leave from 1, and again sharply 3 you have to join in the meeting. Okay, thank you all, thank you so much.
Thank you, sir. Thank you.
Thank you, sir.
Okay, thank you. Madam, thank you so much, madam.